In this lesson, we are going to talk about applications of polynomial, rational, and radical equations. Here we have a polynomial. We may want to look at the graph to decide when the polynomial is positive. For example, it is positive in this section of domain and in that section of domain, or worse, negative here and there. Some other applications may involve work-related problems or motion problems. Here we have a motion problem that you may want to drive the information from this picture and solve it by yourself. Usually work or motion problems result in rational equations that we need to solve. And also we're going to talk about radical equations. So here we have a picture of funny clock with radicals rather than regular numbers. The first application is about work. An experienced painter and an apprentice can paint a room in 6 hours. Working alone, it takes the apprentice 5 hours less than twice the time needed for the experienced painter to paint the room. How long does it take the experienced painter to paint the room? So our whole job to perform is to paint the room. In work-related problems, we're going to use a relation rate times time equals job done. So it's very similar to motion problems when you have rate times time equals distance. However, this distance is actually the job that we need to do. So let's try to analyze the information and organize it in a table like this, where in the top we'll have information about painter, and in the next row, apprentice. Now, what do we know about them? Painter and apprentice together. Okay, so we need another row that will gather information about them working together. If they work together, it takes them 6 hours. So the time for working together is 6 hours. Working alone, it takes the apprentice 5 hours less than twice the time needed by the experienced painter. Now, the question is, how long does it take the experienced painter? So that will be the unknown that we need to solve for. Let's call it t, the time needed for painter. So if time needed for painter is t, we can develop expression for time needed for apprentice to finish the job. The question says that the apprentice needs 5 hours less than twice the time needed for the painter. So 5 less than twice the time needed for painter. So it's altogether 2t minus 5. Now we have the time column filled up. We're talking about the same job to do, so this is one whole job to do for both painter, apprentice, and when they work together. Now from the formula that we see at the top, we can develop rate as one job to do over a certain time. So in the first column we'll have 1 over t, 1 over 2t minus 5, and 1 over 6. And that's how we develop the equation that will be rational equation to solve, because the rate of performing the job by the painter plus the rate of performing the job by his apprentice is equal to the rate when they work together. So let's write down this equation. 1 over t plus 1 over 2t minus 5 equals 1 over 6. And now let's recall how do we solve rational equations? By multiplying everything by common denominator, which is 6t and a bracket 2t minus 5. After multiplying, the denominators will be reduced. So in the first fraction the t will be reduced and we end up with 6 times the bracket. In the second fraction the bracket will be reduced, so we end up with just 6t. And finally the 6 will be reduced, so you end up with t times the bracket. Now the next step will be to open all the brackets and collect like terms to one side. That will be 12t minus 30 plus 6t equals 2t squared minus 5t. When we collect everything, let's say to the right side, we have 2t squared. Then we have 18 on this side, bring it over, will be minus 18, and minus 5 is altogether minus 23t. And finally, plus 30 equals 0. At this point, we can attempt to factor the quadratic trinomial. And if factoring will be too difficult, we could use quadratic formula. But let's see if we could actually factor 2t times t. This is a must. Now we want to multiply this number times that number to get 30, and the middle term must be the sum of these two products, inside and outside product. So, if I put 10 here and 3 there, let's see what will happen. This is 3t, that one is 20t. Oh, there is 23, so yes, that's good. But both of them needs to be negative to obtain negative 23. Yes, it is factored, great. So, t from the first bracket could be 3/2, or t from the second bracket could be 10. Okay, so which one should we take? Well, let's go back to the expression that represent time for the apprentice. This time must be positive. So let's check. If I would take t equals 3/2, then the expression 2 times 3/2 minus 5, when 2 cancels, you have 3 minus 5 is negative 2. We can't take negative 2 for time of the apprentice. The time must be positive, so this root can't be taken. Okay, therefore 10 is our answer. 3/2 is not good because it doesn't satisfy our conditions, and 10 seems to be okay because 2 times 10 is 20 minus 5, it could be 15. 15 hours for apprentice and 10 hours for painter. So now it's time to answer the question, how long does it take the experienced painter to paint the room? And our answer is the painter needs 10 hours to paint the room. The following problem will involve solving radical equations as well as quadratic equation. It will also refer to the well-known Pythagorean equation. So let's see what we have here. A power station is on one side of a river that is 1 mile wide, and we already have the picture that helps us. So river has 1 mile in width. And a factory is 6 miles downstream on the other side of the river. So 6 miles down here, we have a factory on the other side. This distance is 6. The cost is 0.1 million per mile to run power lines over land, and 0.2 million, more expensive, per mile to run power lines underwater. How far over land should the power line be run if the total cost of the project is to be $1 million? So what the question really asks us is, how far we're supposed to go through the land, and at which point we should decide to put the power lines underwater. If we put the power line underwater, we could decrease the distance. However, the expense of putting the line underwater per 1 mile is more than on the ground. So we're kind of looking for a golden solution. We basically need to decide when to turn. Your X could be from here to there, it could be from here to there, and then we could bend it, or we could go till the nearly end, or maybe till the end and then bend it. Well, we don't know which road will be less expensive. It's not how short it is or how long it is, but we need to minimize the cost function. So if you introduce the variable x that will represent the distance from the power station till a certain point where we want to change the direction and put the power line underwater, then in terms of x, cost of laying x miles of power line on the ground is 0.1 times x. The cost per 1 mile, that's in millions, times number of miles x. Now we need to add the cost of putting the power line underwater, but in order to develop this formula we need the distance from P to the factory. So we need this distance. Okay, but this distance can be calculated from Pythagorean equation applied to this triangle. That's a right angle triangle, and we already have some help here on the picture. When you add 1 squared plus 6 minus x squared and take square root of it, that will be the distance d, this distance, that we need to use for the calculation of the cost. So the cost is $0.2 million per each mile, and the number of miles is square root of 1 plus 6 minus x squared. Now the overall cost should be equal to $1 million. So that should be equal to 1, and we are obligated to solve this equation. As you see, this is radical equation, so what we should do is isolate this radical, place the 0.1x to the other side. So we have 0.2 square root of 1 plus 6 minus x squared equals 1 minus 0.1x. Now, since it's not very convenient to have decimals here, I would suggest that we multiply the whole equation by 10 to get rid of those decimals. So we end up with 2 times the root of, and in the meantime we could square this bracket, so it's 1 plus 36 minus 12x plus x squared equals, and that will be 10 minus 1x. Next we would like to square both sides of this equation, so we end up with 4 times everything what's in the bracket. Let's put this together, 37 minus 12x plus x squared. On the other side we need to apply quadratic formula, so it's 100 minus 20x plus x squared. Now we see that we have a polynomial equation, actually a quadratic equation. Let's open this bracket first. So we have 148 minus 48x plus 4x squared, and let's bring those terms to the other side. So we have such equation. Collect like terms, we end up with 3x squared minus 48 plus 20 is 28x, and then we have 148 minus 100 is plus 48 equals 0. Now to check if this is possible to factor, it's a good idea to calculate discriminant. It could be useful either for factoring or for quadratic formula, so it's always good to check that one. So we have b squared, 28 squared, which is 784, minus 4 times 3, which is 12, times 48. Altogether, that turns out to be 208. And since 208 is not a perfect square number, we actually need to use quadratic formula. We won't be able to factor in rational numbers. So our possible roots x1 or 2 are negative b, which is 28, plus or minus square root of delta, which is 208, over 2a, which is 6. So we may want to simplify this root 208. If I break 208 using factor 3, that gives me 2 times 104. 104 is 2 times 52. 52 is 2 times 26. and 26 is 2 times 13. So I have 2 to the 4, which means I could take 4 out of the root, because that's 16, and 13 has to still stay under the root. Everything over 6. I could simplify everything by 2 by factoring the 2 out and reducing. So after reduction, I will end up with 14 plus minus 2 root 13 over 3. So yes, we will get the exact answer, but in this particular word problem, we really need to know approximately how many miles. So it's okay to use calculator and give the approximate answer, maybe up to 2 decimal places. So if we go 14 plus 2 root 13 over 3, we end up with 7.07 miles. Or if we go with 14 minus 2 root 13 divided by 3, ends up to be approximately 226 miles. So which number should we actually take for the final answer? Well, let's look at the problem again. What x represents? It's a distance from the power station till some point P. But we introduced this variable thinking about x as a distance not longer than 6, because otherwise the expression 6 minus x would be negative. Therefore, keep in mind that x is actually between 0 and 6. So if x is smaller than 6, our answer will have to be 2.26. 7.07 would indicate that we would have to go farther than 6, somewhere there, and then going back through the water to the factory. Obviously that wouldn't make much sense, because instead of going so far, we could bend this triangle a lot sooner and decrease the cost. So this is not a good option. So we'll actually follow the road 2.26, which is approximately here, and then bend it underneath the water like this. That will be our least expensive power line. We are ready to give the final answer. How far over the land should the power line run? Well, the power line should run about 2.26 miles over land, then under water. The following application involves using similar triangles. A woodcutter determines the height of a tall tree by first measuring a smaller one 125 feet away, then moving so that his eyes are in the line of sight along the tops of the trees, and measuring how far he is standing from the small tree. Suppose the small tree is 20 feet tall, the man is 25 feet from the small tree, and his eye level is 5 feet above the ground. How tall is the taller tree? So we already have the diagram here. The man is 5 feet tall. He is 25 feet away from the small tree. The distance between the two trees is 125 feet here, and the smaller tree is exactly 20 feet tall. We're wondering what is the height of the larger tree. Let this height be called h. I would suggest that we extend this horizontal line at the 5 feet level to create two right-angle triangles, the small one here and the large one over there. Now let's introduce another variable, call it x. This distance, that means the height of the taller tree, but measured from the 5 feet level. So the plan is, if we figure out what x is, then it's easy to convert it to h, as h would be the same as x plus 5. So now look at the two similar triangles, the big one purple and the small red one. So recall that for similar triangles, the ratios of corresponding sides are equal. In order to use this property, we need this distance. So what is that distance? The whole tree is 20 and this is 5. Therefore, 20 minus 5, this must be 15. Even though it doesn't look like on the picture, but according to the data, this distance is 15. And that distance is 25 from here to there. Also, this distance is known as 125 from here to there. Okay, so we can set up the proportion x over 15 is the same as this side that corresponds to that side. This total side is 25 plus 125, so it's altogether 150 over the smaller side, which is just 25. Solving this proportion, we start with x, we multiply whatever you see across, so 15 times 150, and divide by the number that we didn't use before, by 25. Now we can reduce 25 with 150, leaving us with 6, and then 6 times 15 is 90. So we know that x, this distance, is 90 feet. Therefore, the final answer, how tall is the taller tree? The taller tree is 90 plus this extra 5, so it's 95 feet tall. This example will involve solving equations with rational exponents. The average daily food consumption F of a herbivorous mammal with body weight x, where F and x are measured in pounds, is given by the equation, and here is our equation. Find the weight x of an elephant that consumes 300 pounds of food per day. So basically we need to just plug it in all the information to the formula that is given. So the food consumption is 300 pounds. F of x is 300 equals 0.3 x to the 3/4. And we're solving for x, which represents the weight of the elephant. Okay, how do we solve it? Well, let's get closer to the x, so divide the whole equation by 0.3. That leaves us with 1,000 equals x to the 3/4. And now to reach the x by itself, we need to raise both sides of the equation to the reciprocal of this exponent, to the 4/3, in order to cancel the 3/4. So the 3/4 will be reduced and we end up with final answer. The x should be 1,000 to the 4/3. Now to evaluate it even without calculator, change 1,000 to the power of 10 form. So that's 10 to the 3 and then is raised to the 4/3. Now the 3 with the 3 will be reduced, so you end up with x equals 10 to the 4, which is 10,000 pounds. So the elephant weighs 10,000 pounds. Last example involves some geometrical shapes. A storage bin for corn consists of a cylindrical section made of wire mesh, surmounted by a conical tin roof. The height of the roof is 1/3 the height of the entire structure. If the total volume of the structure is 1400 pi feet cube and its radius is 10 feet, what is its height? So here we have two shapes, a cylinder with the circle in a base, and the circle has radius 10 feet. Radius 10 feet. Now the height of entire structure is marked by small h. We're going to need the height of the cylinder as well, which is from here to there. So to distinguish it from small h, let's call it capital H. And then the relation between capital H and H is the capital H is the same as, if this is 1/3 of small h, that will be 2/3 of small h. So capital H is 2/3 of small h. That will be needed for finding out the volume. The problem also gives us the overall volume of the storage bin. So the equation that we need to develop is the one that will compare the volumes. So volume of the cylinder plus volume of the cone should be equal to the overall volume 1400 pi feet cubed. Now, what is the formula for volume of a cylinder? It's area of the base times its height. Area of the base is pi r square times this capital H. Then the volume of the cone is 1/3 of area of the base, and again area of the base is pi r square, times this height of the cone, which is 1/3 of small h. This whole thing is 1400 pi. Now what's left to do is to convert this capital H into small h by using this relation, and to plug it in the value for radius, which is 10 feet. So pi times 10 squared is 100. Capital H is 2/3 h, plus 1/3 times 1/3 will be 1/9 times pi, and r squared again is 100, and h equals 1400 pi. We're solving for h, so we have some fractions here. Maybe it's a good idea to multiply the whole equation by 9 and at the same time divide the whole equation by pi. So get rid of pi, multiply by 9 to get rid of fractions. We end up with 9 divided by 3 is 3 times 2 is 6 times 100, 600h, plus 9 divided by 9 disappears, so we have just 100h. And finally 9 times 14 is 126 and 2 zeros. Now it's good to decrease those coefficients by dividing by 100, meaning drop all those 2 zeros. And we end up with 6h plus 1h is 7h equals 126. Therefore h equals 126/7, which turns out to be 18. So the height should be of 18 feet. Give the formal answer. The height of the storage is 18 feet. And that was the last example in this lesson.